Okay, I want to talk today about chapter 18. So this is the topic for chapter 18 is constrained optimization. So in this particular segment, I'll talk about constrained optimization and general constrained optimization problems. Okay, constrained optimization. Okay, so the idea in chapter 14, we talked about unconstrained optimization problems, problems of the form, minimize f of x, where x is in all of Rn, right? So this is an unconstrained problem. X can be anything. In chapter 18, we focus on constrained optimization problems. So for example, if these are level curves of the objective function, so this is, these are f of x is some constant level curves, and let's say the level curves are increasing in this direction, then the optimum, the unconstrained optimum, would be x star, okay, right here at the center. It's at the minimum of these things. But if the problem is constrained, so for example, if the state x has to stay within this feasible region, then you can see that the minimum is going to be down here at x plus. So the constrained optimum x plus is going to be different than the unconstrained optimum x star. And you'll also notice that the constrained optimum in this particular case is at a boundary point. And that will inform some of the things that we talk about. Okay, so the constrained and unconstrained optimum may be different. All right, so we need to talk about all this, we need some definitions. So let's start out, we'll use omega to indicate the set of Rn that is feasible. So for example, if you're on the real line, omega may be some subset of the real line. So omega is the feasible region. Then x star in omega is a local minimum of f over omega if there exists an epsilon such that x's and omega intersect, and this is an epsilon ball, so this is actually, that should be a y. It's the set of all, this is basically, a ball of epsilon around x star, right? It's all of the elements of Rn that are within epsilon of x star. Okay, if when we look at all of the x's in omega intersect an epsilon ball, if f of x star is the smallest, or at least less than or equal to all other f of x, then it's a local minimum. So for example, down here at the bottom we have this is going to be a local minimum because we can find an epsilon ball where this is the smallest element of all of the f is smallest at that point. This is also a local minimum here because again we can find an epsilon ball here where f at that point is smaller than all of the f at all of the points locally. So this is also, all of these points here would be local minimum because it's a less than or equal to sign here. So again, you can find an epsilon ball around any of these points where f of x is, greater than or equal to f of x star. And so it's a local minimum. And one of the elements that's different than in constrained optimization than unconstrained is that a point like this may also be a local minimum, okay? Even if f, let's say, continues down like this. Because we're constrained on omega, when we take an epsilon ball and intersect it with omega, we're just looking at these points, right? And so for every x in that region, f of x star here would be smaller than all of the f of x over that region. So this point may also be a local minimum. Okay, and then if f of x is greater than f of x star, then we call it a strict local minimum. So this would be a strict local minimum, a strict local minimum, a strict local minimum, but this would not be, these elements here would not be strict local minimum because we don't have strictly f of x strictly greater than f of x star. We only have it less than or greater than or equal. And if we can pick, epsilon arbitrarily large, then we get a global minimum. So this is the only global minimum because, we pick epsilon arbitrarily large, and this is the only point that's smaller than everything shown here. Okay, so these are definitions. We need a few more definitions. So the idea that we're going at here is, let's suppose this is, omega. We want to talk about, first of all, we have a feasible point. So we say that that this point here, x, is a feasible point if, if it's inside of omega. So x is in omega implies x is feasible. Okay, so this feasible direction, I don't know, this is kind of confusing. We say that that a vector d, okay, and d here is going to be in Rn. We say that d is a feasible direction at x if there exists an epsilon naught so that x plus epsilon d is in omega for every epsilon between 0 and epsilon naught. So in other words, this a vector d, let's say in that direction, is going to be a feasible direction because there's some scalar so that f plus epsilon x naught. See, epsilon naught would be right here at the boundary. So that scalar of d is inside of omega, and everything smaller than that. So we have epsilon, everything smaller than epsilon naught is also inside of omega. And so actually, any direction to these interior points is going to be a feasible direction. But if we're on the border, let's say we're right here, then we have feasible directions, but this would not be a feasible direction because there's no epsilon that will allow us to move in that direction. So we only have these feasible directions. Now, if we have a concave function like this, we may have d would go like that. So there may be large epsilons that get us inside of omega, but that's not a feasible direction because it has to be, for some epsilon, it has to be true for epsilon naught, it has to be true for every epsilon less than that. So the only feasible directions, would be things that point interior to that to that point x. Okay, so that's a feasible direction. All right, now we need to recall taking the gradient of a vector. So again, if we have f is from Rn to R, then when we take the gradient of f, we get a column vector. And the Hessian is going to be, will look like this. And basically, we're going to take the partial of f1 and now take the partial with respect to x1, x2, x3, etc. And the Hessian matrix, if we also have this thing that if f is C3, in other words, it's you can differentiate 3 times and you still get a continuous function, then in this case, when we take the second partial of f, with respect to, let's say, x1, and then take the partial with respect to x2, that's the same thing as taking the partial with respect to x2 and then the partial with respect to x1. So this is a basic thing that you prove in, for example, multivariable calculus, and that means that the Hessian is symmetric. So in other words, this if you call this H, then H is equal to H transpose. The Hessian will be symmetric. All right, so in the unconstrained case, we know that, so in other words, that when omega is equal to Rn, then a necessary condition for x star to be a local minimum is that the gradient is 0. And then a sufficient condition is that the Hessian is positive definite. That would be for a local minimum. And for a local maximum, it would be that the Hessian is negative definite. Okay, what about constrained optimization problems? Do we have anything that looks like this? Okay, so the answer is sort of yes. We do have something, but it is a little bit different. Okay, so let's suppose that omega is our constrained set, and again, F maps Rn to R, and it's continuously differentiable, meaning that you can differentiate once and you still get a continuous function. All right, if x star is a local minimum of F over omega, so this is a constrained local minimum, then for any feasible direction D, we have that the gradient, the inner product of the gradient and D is positive. So again, there's a picture here. You can think of the level curves. The gradient goes out, and if you have if we have some kind of constraint, so let's say our constraint set goes like this, so this is omega, then the local minimum would be at this point, the gradient would point like that, and of course for any feasible direction D, we have to have a positive inner product. So feasible directions that go like that would give you a negative inner product. And so, basically, so we have this theorem that says that the inner product of the gradient with feasible directions has to always be positive. Now, if F, and that's always, let's see, so that's always true, then we also can say that if x star is an interior point, then the gradient has to be equal to 0. And we can say that, so that these are the necessary conditions. And then we can say that if in addition, if F is C2, so we can differentiate twice and we get a continuous function, then, and we know that the gradient inner product with D is 0, then for those particular D's where we have the inner product here is equal to 0, then the Hessian is positive. This looks like positive definite, but positive definite would say that this is true for every D. Our sufficient condition here says that this is true only for those D's where the inner product with the gradient is equal to 0. And this is certainly a weaker condition than positive semi-definite, because this doesn't say the Hessian's positive semi-definite. It just says it's positive, this quadratic form is positive for those D's that satisfy this condition. Okay, so how would we go about proving each of these statements? So the first thing we want to do is prove that this is true for any local minimum. Okay, we prove it by taking Taylor series expansion. So if you look at f around, let's say x star is our local minimum, then f of x star plus epsilon d is going to be f of x star, and then we're going to have the gradient transpose with d times epsilon, and then all of the higher order terms, which are, or O of epsilon, meaning they, if you divide by epsilon, if you divide this by epsilon, it goes to 0, as epsilon goes to 0. Okay, so that means if we move this to the other side, we've got this guy. So when epsilon gets small, this guy goes to 0, and we have to have that, since it's a local minimum, we have to have that this is positive. And that implies that, and it's going to be positive for every epsilon. So that means that we have to have that the gradient is positive. So this guy's going to be positive, so this gradient here has to be positive. So that's the proof of item 1. Now, if it's an interior point, okay, by interior point we mean, this is omega and x star is inside. It's not on the boundary. Now, in that case, that's we have that, every direction is feasible. So we have to have that the inner product of the gradient with d is, we know that it's positive for every d, right? So if it's positive for that d, and then it also has to be greater than or equal to this d, it also has to be greater than or equal to that d. So we just use that fact. It has to be greater than or equal to d, and also greater than or equal for negative d. And that means, since if we have a is greater than or equal to 0 and minus a is greater than or equal to 0, these two together imply that a has to equal 0. So we have to have then that this is equal to 0, and that has to be true for every single d. And since it's true for every d, then this guy, in fact, has to be equal to 0. So if it's an interior point, then in fact the gradient at that point is equal to 0. So, and this comes back to, in other words, interior points just look like unconstrained optimization problems. Okay, now if we know that the inner product of the gradient with a feasible direction is equal to 0, we can look at the Taylor series expansion. And in the Taylor series expansion, in this particular case, that epsilon times d transpose the gradient, that's equal to 0. So what we're left with is just the second derivative here. And that'll have an epsilon squared, and then all of the higher order terms are going to be O of epsilon squared, meaning if we divide by epsilon squared and let epsilon go to 0, this term goes to 0. So when we pull this to the other side, it's a local minimum, so this guy has to be positive, and it has to be true for every epsilon, so we let epsilon go to 0, this term goes away, and this term basically looks like, this guy has to be positive. So this thing has to be positive for every d where the gradient is equal to 0. And the idea is that, if we have this, again, omega might look something like this, and then our feasible directions are going to be, let's say, if the gradient is, I guess in this particular case, the gradient, so, this is the gradient here, partial, del f at x star, and then feasible, in the feasible, in other words, if you look at this feasible direction where this is, where the inner product is equal to 0, so for these particular d's, we have to have that d transpose, the Hessian, is positive. Okay. All right, so now you might ask, are there sufficient conditions? First, suppose that the constraints are not active. So when x star is an interior point, what do things look like? And here we have this theorem by Moon. Okay, I'm going to actually stop here and make another movie. Okay, so are there sufficient conditions for constrained optimum? Much like with the unconstrained optimum, we have, again, the positive definiteness or negative definiteness of the Hessian. Okay, so first suppose that the constraints are not active. In this case, x star is an interior point, and we'll consider the active constraints later. So here is theorem 18.2 for Moon. If f is two times continuously differentiable, meaning you can differentiate twice and still have a continuous function on omega, and let x star be an interior point. If the gradient is 0 and the Hessian is positive definite, then x star is a strict local minimum of f. So this is an interior point, looks exactly like the unconstrained case. And how do you prove it? Well, again, you take the Taylor series expansion here. So we've got x star, and if we move some epsilon in the direction of d, then here's our Taylor series expansion. And you notice if we move this to the other side, then since the gradient is 0, we just have this second order term. And since it's a local minimum, this thing needs to be positive for every epsilon. So when epsilon gets small, this thing sort of gets smaller. The effect gets smaller and smaller, much faster than epsilon squared, because since it's O of epsilon squared, when we divide by epsilon squared, this term is alone, and let epsilon go to 0, or go to infinity, or to go to 0, then this term goes to 0. So that means that this term has to be positive. And since it's an interior point, it has to be positive for every d. That means the Hessian has to be positive. Positive definite. And so if it's positive definite, actually, we're doing a sufficient condition. If this thing is positive definite, then we know that f of x star plus epsilon d is bigger than f of x star for every direction. And so it's a strict local minimum. So this says we cannot generalize this theorem to the case when this is positive semi-definite. And why is that? So if this is positive semi-definite, then we may have a 0, and then this term up here, the third order term, could be positive or negative. And so we can't guarantee that it's going to be positive definite. Okay, so I want to finish up by just talking about general constrained optimization problems. So with general constrained optimization, we have two different types of constraints. We have equality constraints and inequality constraints. So equality constraints look like the following. H of I, this would be the ith constraint of x, is equal to 0. So equality, meaning this thing is equal to 0. So for example, if I said x1 squared, if it's a third order, it's x1 squared, x1, 2, x1, x2, x3 plus tangent x3 cosine x2, I just made that up, is equal to 0. This would be an equality constraint. Okay? Inequality constraints, on the other hand, look like this. Gi of x less than or equal to 0. So for example, if we wanted, if we wanted to say, okay, let's do optimization over, the positive quadrant, where, this is x1 and x2, so x1 and x2 both greater than or equal to 0, like this, these quantities here. We could write it in this form by saying, okay, x1 greater than or equal to 0 means minus x1 is less than or equal to 0. So g1 would be minus, this function would be minus x1, and g2 would be minus x2. So we can always write it in this form, gi less than or equal to 0. Okay, so equality constraints are always written like this. Inequality constraints are always written like this, with the less than or equal to 0. So we can always take regions, any region omega can always be described by inequality constraints by just looking at the boundary. So here's a some kind of polygon can be written in terms of linear constraints. So if we have, this hyperplane described by n1, in other words, this hyperplane is going to be x minus y1 being any point, any point on the hyperplane. X minus y1 transpose times n1 would be everything. In other words, this term is orthogonal to n1. So any vector out here that's orthogonal to n1, that would be, if this was equal, that would give you the hyperplane. And now if this term is less than or equal to 0, then it's everything to the left, or to the, on the opposite direction of n1. And then n2 would be the opposite direction of n2, and 3, would similarly. So omega would be, something that looks like this, given these inequality constraints. Okay, so in general, a general constrained optimization problem can be written as follows. We want to minimize f of x for all x and omega such that equality maybe m equality constraints are satisfied and p inequality constraints are satisfied. This would be your general nonlinear constrained optimization problem. And since it's kind of awkward to write kind of everything out, what we do is collect all of the equality constraints in H and all of the inequality constraints in G, and we write our general optimization problem like this. We want to minimize f of x such that equality constraints are satisfied and a set of inequality constraints are satisfied. Okay, so what we're going to do the rest of the semester, or the rest of the chapter, in the semester, is to look at equality constraints and inequality constraints. So equality constraints, it turns out, are much easier to deal with than inequality. So we will work first of all on equality constraints, and then we'll go to inequality constraints.